Okay, continue with our previous video. So remember that's our discussion question, right? So we have our hypothesis, no hypothesis writing on the same portion of people prefer super as rival. So the alternative hypothesis is a smaller portion of people prefer super. So in our observation data is 91 out of 200 testers prefer super soda. So that's why for our simulation, we use the test statistic is the number of people out of 200 prefer super soda. Then after our simulation for 10,000 times, so that's our empirical distribution. Then we have the yellow line here, that's the 91 is our observed data. So all the area in the yellow side, that's our tail area we want to calculate, so we can know our p-value is. So since that's on the left-hand side, so that's all the data here is smaller than or equal to 91. In order to find the area for this side, we can using the count all the results in the count array, right? So then anyone less than 91, so then we will have true and false. So then after we calculate the non-zero one divided by the total count number, that's 10,000. So then we got 1145. 0.1148. That's about 11.48%. So remember before when we talk about when we make the decision, right? We have two cutoff. You have 1% cutoff, we have 5% cutoff. So this one actually is more than 10%. So how should we write our conclusion for this one? Yeah, so alternative. So we don't favor alternative viewpoints, right? So on the other hand, here the data, the result is consistent with our null hypothesis. So we do not. So usually when we write the conclusion, we just write we reject the null hypothesis or we do not reject. So for this one, we do not reject the null hypothesis. Okay, so this one since that's a cell, so that's make the comment here. Or if you want, you can change this one instead to be a code. So if you want, we can change to the markdown. Okay. So then, yeah. So that's our conclusion. But one thing is, right, so you don't have to put the pound sign. So maybe we just do like this. Okay. Okay, so that's our example for our discussion. Okay, so think about any question about that. Sorry, this is not a live lecture, but if you have any question, discuss with your classmates or post in the our each module we have discussion page, so you can share with that. So some of you, as we know, your question is, remember that's just our one-time simulation, okay? So of course, when we try to make the conclusion, we just try to make our simulation time as large as possible, okay? But one thing is, you will say, how about if I run the simulation again? So that's why here, you have each time you simulate 10,000 times. But of course, if you simulate again, your result maybe will have slightly different. Okay, so then you will see earlier is 11.48, right? So you see now they become 11.4%. So that's why here we want to discuss is, remember, before we talk about, we do need to have the simulation time, the number of your simulation as big as possible. Okay, so one thing is, the reason is, supposedly if you have a big amount of the simulation time, so since you try many times, So that's why our results will be more, the empirical distribution will more fit within the theoretical distribution. Okay, so here, the next one I want to discuss is, will that simulation time, the number of simulation time, how they will affect our result. Okay, so that's why here, that's wrong. This one, for example, here, like earlier I showed you, right? You can rerun, and we need to start from here to rerun the simulation, then get the result. But also one thing is here, that's write the whole simulation and including the p-value testing in one function. Okay, so that's why here we write a function we want to show you is, this function is our simulation run_test function. This one, not only you can specify your sample size, you can specify how many times your simulation you want to do. Okay, so this one actually just control our for loop condition, right? Okay, so then we still have our count arrays, empty array. So every time when we run the simulation, okay, passing the sample size, so then we have our count result. Okay, so here, let's define the function. So then again, you can see here, every time I run, okay, is one time simulation. You simulate 10,000 times, sample size is 200. Then also we show you the p-value. Okay, so on the other hand, right, you see we run many times. So this one I just need to run one cell. Okay, 11, 14. The good thing is you can see they are pretty consistent. They are all around 11 something. Okay, I mean percent. Okay. So of course you can run many times as you want. But one thing is here I want to show you is we want to change the number of the simulation. And also we want to run, because each time when we run the simulation, the same thing, that's still by chance. You just run one time, right? So then how about we compare our result? If I run the simulation, the whole simulation, 50 times. So I want to see, is our result is kind of similar, or they have big range. Because one thing, like we say, you want to do the hypothesis conclusion. We do simulate many times, but we still want to know when we make the decision, is the reasonable decision, or it's just by chance, is a special case or something. We do want to know every time when we run the simulation before we make the conclusion, our result is really close to the population. Okay, so that's why here we want to show you in this part is we will change the number of your simulation. I simulate, this one I simulate 10,000 times, right? So you can see here, if I change to 1,000 times, then I can run. Wow, you can see they change dramatically already. They are now around 11%. They do have 11%. Okay, but then you can see they have 10%. They have 12%. They have 10%. Yeah, so that's why you see every time you run. So then if you change to 1,000, they have bigger range for their result. So how about we change to 100%? 11, good. Okay, still 11. Oh yeah, then they drop to 6%. That's 10%, 9%, 12%. Okay. So that's why we don't want to manually run, right? But from this manually run, you can see if the simulation size change become 100, the range is quite big, from 5% to 14%. Okay, so that's why here, again, using this example, that's right. The other one is we want to see a result. We want to compare the simulation times is different. We have 10 times. We have 1,000 times. We have 10,000 times compared to our p-value result. So each simulation, I not only run one time. That's run each sample simulation times 50 times. Okay, so each one here, yeah, is according to 100 So actually each iteration I run simulation 100 times, 1000 times, and 10,000 times. Okay, so then I repeat 50 times, and each time I also calculate the p-value. So that's why we just show the first 3 columns. So you can see the first iteration. Then you can see actually it takes a little while to finish because we need to do this one on the 10,000 times simulation. It's not only one simulation, right? We do 50 times simulation. Okay, good, finish. Okay. Okay, so here 1, 2, 3. Actually here is still the same thing. They finished the 100 first. Okay, so do the 50 times is 100. So then but let's show you one thing. Let's show you. Okay, let's show the whole thing, but then we need to run again. Okay, let me pause so you don't need to wait so long. So just correction, earlier actually I say actually it's 100 simulation, they run 50 times, then 1,000, then 10,000. So that's why you can see here. So for 100, the first 50 times, they have bigger range, right? So now so far see 17 or 18. Okay, the small one we even have I think the smallest one is 6. Okay, so that's why you can see they have even 0.2, 20%. Okay, so then change to 1,000. 1,000 is not too bad. They're still between 10 to 12%. Okay. So then you can see, right, for 10,000, they are all like 11% something. Okay, so of course, you can see the result. I just want to show the whole table. But one thing is, the most important thing, we don't want to just see the table by ourselves, right? Actually, we got a simulation result. Yeah, that's group. Okay, so this one is, we can group our test result using the simulation time. So then they will show you the histogram. So in this histogram, what did you see? Okay, so the dark blue is your simulation time is 100. So that's why we say they have bigger range. If your p-value is you see, if your p-value is under 0.45, 0.055%, we need to reject, right? But they also have a lot of amount is like a way not to reject. Okay, so then you see the yellow one. Yellow one, okay, if we still have 5% is our cutoff. Okay, so they are still in that range, but their range is much bigger. Much less than 100, but bigger than the 10,000. But you can see 10,000 actually is more consistent. They are almost all the time is within 11%, just a little bit 12%. So this one shows us what? Remember, before we told you, the simulation we want, you need to make sure you do as much time as you can. Because if the simulation time is bigger, they will have more, the empirical distribution will more close to the population distribution. If not, if the sample size, the simulation time is a little smaller, they kind of have wider range. So this one actually we can see you even, this one is we just compare 50 times from 3 different simulation times, right? Even by the same simulation, okay? So this one we just see, let me still have this one. We do simulation, you see, if we do 10,000 times, then we run each one, we run, let me run small one first, because that will be faster. So in this cell, we just run, you can decide your simulation time. Then we run each simulation 200 times. We see we compare 2 different results. Okay, so this one actually, your first blue is you do the 200 times distribution. And the second one, the yellow, is also do the 100 distribution. But 100 times simulation. But you can see they're not really covered by each other. So that's why even by itself, they have very varied for the 2 sets. but then you change to the size is 1000. Okay, you see they cover better. Okay, so that's more consistent. Of course, if you change to the 10,000, we need to wait for a little bit. But one thing that yeah, not too bad. Okay, so that's why you can see they are more consistent for each set of the testing. Okay, I will discuss with this issue more in the next video. So I will stop here. I'll just show you the result.